Okay, so it's time to start again, I think. So today I will focus on tropical polynomials and plane curves, and we'll start really with the very beginnings for each of those of you who have not yet heard anything about tropical geometry. And I want to mention that there are notes that Renzo actually provided, and I think Vance agreed to make them available on the same webpage as the exercises from Renzo's course. There you will also find notes for this talk. So not only for this talk, for this lecture series about Kontsevich formula in the tropical world. Okay, so we want to start with an intrinsic point of view, so to say. We forget about algebraic geometry for the moment, and we just start as tropical geometers, so to say. And I told you that you can think of tropical geometry as geometry over the max plus semi-field. So what is the max plus semi-field actually? As the set of numbers, I take R union minus infinity. Then as my addition, I take the maximum. And as my multiplication, I take plus. And then you see immediately that minus infinity, so let me write, this is the tropical semi-field. Tropical semi-field, or max plus semi-field, it is also called max plus semi-field. And of course there's a min version, and this is just a taste. Yes, please.
Could you not use green?
Could I not use green? I can try to avoid it. It's not that easy, maybe, but okay, let me try with this one. I hope this will be better. Okay. Okay, so you see immediately that minus infinity is the additive inverse. That's better, huh? Yeah. Minus infinity is the additive neutral. 0 is the multiplicative neutral. So it takes some getting used to this funny way of computing, but it works, right? You also have inverses for the tropical multiplication, because they are just the additive inverses in the usual world. That's no problem. But what's a bit sad, this is why it's only a semi-field, there are no inverses for addition, right? If you want to solve the equation, so let me write no inverses for addition. If we want to solve the equation x tropical plus a equal minus infinity, I should have told you this maximum is called the tropical plus. We can make a circle around it to distinguish it from the usual operations. This is the tropical times, also a circle around it. So x tropical plus a equal minus infinity means the maximum of x and a should be minus infinity. I have a fixed a I want to solve for x, it doesn't work, right? So in general, we do not have inverses for addition, meaning we cannot subtract in the tropical semi-field, which is a bit sad, but okay, that's how it is. Okay, but what can we do, and what do we want to do, right? We want to do, in a sense, algebraic geometry over this tropical semi-field. And what is algebraic geometry? We're studying vanishing loci of polynomials, right? So the first thing to understand, what are polynomials in the tropical world? And what are polynomials? Well, in general, so let me write definition. Tropical polynomials well, usually a polynomial is just this finite sum, and now we're just taking a tropical sum over some finite set of alpha in n to the n. Then we have coefficients for each term, and then we have, the monomial, x1 to the alpha 1 times, and so on, times xn to the alpha n. And this, to the notation, is supposed to be a tropical power here, of course, yet again, right, everything tropical. So let's translate this. What do we really mean? This big sum here is going to become a big maximum, right? And then all these times are going to be pluses, so we have a alpha plus, and then here, this tropical power, we take x1 tropical times, alpha 1 times, but that's x1 plus x1 plus x1, and so on, alpha 1 times, so that's nothing else but alpha 1 x1, and so on, up to alpha n xn. So if we just restrict to a monomial, you see immediately that you're getting a linear function, or an affine linear function. You can view it as an affine linear function from R to the n to R. Yeah, and the polynomial is then a piecewise linear function with finitely many pieces. So it gives a piecewise linear function maybe I should write from R to the n to R with finitely many pieces. Okay, so you see already that polynomials become something that is piecewise linear, and that is of course what is attractive in the tropical world, that you're being in the linear world, which in general can be viewed as something easier maybe than the polynomial world, because linear equations are easy to solve, of course. One thing to point out is that polynomials and polynomial functions are not the same. If you have a field with infinite elements, for usual polynomials, this is the case, so we can usually identify a polynomial function with a polynomial, but this is not true in the tropical world. So, for example, if we consider this polynomial 0 plus minus 1 times x plus x squared, and the polynomial 0 plus x squared, then what is happening? So I've chosen a univariate polynomial so that I can actually easily draw the graph of these as piecewise linear functions. And I always find it easy to draw the graphs as piecewise linear functions by first drawing the linear pieces and then deciding where the max is going to be. So what are the linear pieces here? I have one term is just 0, right? The other term minus 1 plus x, so that will look something like this. And then I have x squared, which will sort of look something like this. And then you see, just looking at it, the max is here, right? So this is the graph of my tropical polynomial f1. And I think you see immediately that that middle term does not contribute anything. And so leaving it out in this second polynomial here will give the same function, even though it's a different polynomial. So you have to pay a little bit attention with those tropical polynomials. They don't behave exactly as we think they should behave, but nevertheless, they are nice. Okay, so we have polynomials. We want to go for geometry. We want to study vanishing loci. What is the problem about that? If we study a vanishing locus, we set, for example, one polynomial equation to be 0, right? But then we need to subtract if we want to solve somehow. And subtraction we don't have. So defining zeros of a tropical polynomial is actually not completely obvious how you should do that. And here's one example that helps you to understand this. Let's discuss univariate cubic polynomials. So they are of the form a times x cubed plus b times x squared plus c times x plus d for some numbers, a, b, c, and d. And I want to assume that d minus c is less than or equal to c minus b is less than or equal to b minus a. And that is the condition that is needed to guarantee that somehow all three pieces, or all four pieces are visible. Yeah? So if I make a rough sketch about what is going on, somewhere, take the other color again. Somewhere is this term d, right, which is just constant. And then I have a linear term somewhere, okay, c times x, c plus x, of course. Then I have this quadratic term, a little steeper. And then I have a really steep cubic term, so it looks like this. And this position at where the two loci meet is precisely at d minus c here. This is at c minus b. And this is at b minus a. Yeah, and so requiring this inequality makes sure that actually all four pieces are visible. All four pieces actually contribute to this piecewise linear function, which is my cubic tropical polynomial. And Oopsie. Sorry, that picture went completely wrong. Sorry. This was supposed to be that point where the linear term and the quadratic term intersect, and this was supposed to be this point. So, okay, so this is c minus b. Yeah, okay. Yeah, did you see it? Good. Okay, so these corner loci, where the pieces come together, these actually help you to give you a factorization in linear terms. So you can just compute that this polynomial equals 8 times x plus d minus c times x plus c minus b times x plus b minus a. Yeah, it's just a check, you know, you go through every possible interval that x can be in, and you see where's the maximum taken here and where's the maximum taken here for each of those summons, for each of those, classical summons, tropical factors, right? And then you see those agree, and that explains why we want to view the corner loci as the roots, respectively zeros, of our polynomial. So corner loci correspond to zeros of the polynomial. Because you know, of course, that a factorization of a univariate polynomial is in terms of the roots of the polynomial, in terms of the zeros. And this is precisely the point of view we want to take here. And now this is something that we can use to actually define hypersurfaces, first of all. So the vanishing locus of a single polynomial. And so I'll define tropical hypersurfaces. And I call it I call it V-trop of a tropical polynomial f, and that is defined to be the set of all x in R to the n, such that the max in f is attained at least twice. Okay, so in this cubic univariate polynomial example, we would be talking about a tropical hypersurface in R, because we're having just one variable, and we would get precisely those 3 points in R as our tropical hypersurface, the points where the maximum is attained not uniquely, not by just one term, but by at least 2 terms, the corner loci of the piecewise linear function. Okay, and this is a tropical hypersurface of f, yeah? And for n equal 2, this is the case we want to focus on here, it's called a tropical plane curve. So let's do an example. Let's do a baby example by taking a linear tropical polynomial in 2 variables. So as I say, I want to focus on the case n equal 2. That first example with n equal 1 was only to be able to actually draw the graphs, right, to make you see something. Now n equal 2, having 2 variables, and I take a linear polynomial, so max of x, y, and 1, let's say. So you can also write it, of course, tropically as x plus y plus 1. So you see immediately it's a tropical linear polynomial. Okay, so it's not super easy to sketch the graph of this in R to the 3, of course. Yeah, I don't think I want to try. What I do is I draw R2, and I give you the regions of polynomiality. Yeah, so it'll look like this. If x is less than or equal to 1 and y is less than or equal to 1, which is going to be this region here, then 1 is the maximum, so this is where this term wins, right? Over here, the term x wins, and over here the term y wins, right? And so the graph in 3 space kind of looks like something like this, yeah? So this is lifted to constant height. This ray goes diagonally up, and those two are folded to follow along somehow. Okay, and then we take the corner locus. So we just take the picture that I've already drawn. Here we have x is equal to 1 is bigger or equal to y. Here we have x is equal to y is bigger or equal to 1. And here we have y is equal to 1 is bigger or equal to x. So those 3 rays together is precisely all points x, y in R2, where the maximum is not attained uniquely, but attained by at least 2 terms. And this is what we call a tropical line, because it's given by the vanishing locus, or the tropical hypersurface of a linear tropical polynomial. So it's a tropical line. Okay, more generally, and this is something you might want to try in your exercise sessions, if you change the coefficients. So let's do the max of a plus x, b plus y, c. Yeah? So here I had the coefficients 0, 0, 1. Now I take a, b, c instead. What's happening? I'm going to get sort of the same picture, except the vertex of this 3 rays is going to be shifted. It's going to be at c minus a, c minus b. But in general, this is how a tropical line looks like. You always have those 3 rays meeting at one point, and you can just shift this picture around to get different lines. Okay, this is good, because now we can do our first sanity check, so to say, which is if you give me 2 points and ask me to draw a tropical line through it, then most likely I will find precisely 1 tropical line through 2 points. Yeah, so that's good, because we want that. We want a line to be defined by 2 different points, okay, or by 2 generic points, maybe I should say. Also, if we take 2 lines, then most likely they intersect in just 1 point. Also good. Yeah. Yet again, this is generic behavior, but nevertheless, generally the tropical lines behave as we want them to behave, and that means we are on the right track somehow. We're not doing something stupid by trying to do algebraic geometry over this tropical semi-field, but we're getting somewhere. Okay, so just to fix some notation, let's assume we have a polyhedron in P. A question? Yeah.
So tropical line because the coefficient of x, y is 1. What's the definition of tropical line?
The exponent. I want the power here to be 1. Yeah? That's tropical line in the plane. Yeah? Yeah? Sure, no problem. Okay, so we take a polyhedron, P, in R to the n, and we take a functional in the dual space, and then we define the face, just to set notation, yeah? The face corresponding to this functional w of P to be the set of all x in P, such that w times x is bigger or equal to w times y for all y in P. Yeah? So the face at which w is maximized, at which this functional w wins, right? That is this face. And then we can define the outer normal fan of a polytope. Of a polytope P. And we call it NP. And it consists of all cones of the form NP of F, where F is a face of my polytope, and in P of F consists of all functionals in the dual space, such that the face of this functional equals F. And then this would define an open cone, but we want closed cones in our fan, so we take the closure of this, and F, as I said, is a face of P. Yeah, of course you have to show that this is actually a fan, but let me just draw some pictures to help you get intuition, if you don't know this already, how this looks like. So this is my polytope in 2 space, okay? And now let me think about all W that will make this face maximize? Well, I have to take something that is orthogonal on this face, right? Then this will be maximized. So the length of this vector doesn't play any role, so I'm going to get a ray in that direction. For this face, analogously, I'm getting a downwards ray. For this face, I'm getting this ray. Then if I want to maximize the vertex, I have to take anybody, any hyperplane with a normal vector that is not quite this and not quite this, right? Everyone inside here works. And so this whole interior of this two-dimensional cone would be this thing for f being the vertex without the closure. But then I said already I want closed cones, of course. So I throw in the two boundaries of my open cone, the two rays and the point, of course. And then I have a closed face for this vertex here. And analogously for the other two faces, I get those two cones. So in the two-dimensional world, it is drawing a normal fan is really as easy as just taking the outside normals, yeah, drawing them in the dual space and letting them produce a fan. Yeah, that's the outer normal fan of my polytope. And of course, in the toric world, we often work with inner normal fans just because, but that's the usual min-max problem that we have. And I can tell you already now, there's no way to avoid it. If you live in tropical geometry, you have to live with this choice. And you can't decide to be only one convention forever, because as soon as you start discussing dual problems somehow, you have to live with the other anyway. Okay. So I need to make some space here. So why did I introduce this notation? Because I want to convince you that if I have a tropical polynomial, so let f be a tropical polynomial such that all coefficients are 0. So meaning all coefficients which are not minus infinity. All terms that exist at all, yeah, should have a 0 coefficient. And we also call this the constant coefficient case in tropical geometry. Then the tropical hypersurface, V-trop, for this tropical polynomial f is nothing but the codimension 1 skeleton of the Newton polytope of f. And maybe I should add also, if f is sum over a alpha x to the alpha, all supposed to be tropical, maybe I should write it tropical also, sorry. Sum over a alpha times x to the alpha, then the Newton polytope is the convex hull of all alpha. That appears such that a alpha is not equal to minus infinity. Okay, and of course, the analogous notation also exists for classical polynomials. We also have Newton polytopes for normal polynomials, and it's just the same thing. You only use a alpha not equal to 0 then, because you want only terms which exist. So going back to our tropical line, for example, where f was the max of x, y, and 1. No, actually, let me do x, y, and 0. And I hope I can easily convince you that I can just shift the picture I've drawn around such that 0, 0 is the ray of this, of the tropical line defined by this tropical linear polynomial. And now let's understand the Newton polytope of this tropical polynomial. Well, what are the exponent vectors Here I have x to the 1, y to the 0. So 1, 0 is my exponent vector. So that will be precisely this vertex, right? Y is y to the 1, x to the 0. So 0, 1, x to the 0, y to the 1, sorry, 0, 1 is my exponent vector. That's this here. And 0 is, of course, x to the 0, y to the 0. So this point here. And then the convex hull of those three is precisely the triangle I've drawn. And when you now look at the codimension 1 skeleton of the normal fan, you see that it actually works, that I am correct, that the tropical hypersurface defined by this polynomial is really just the codimension 1 skeleton of this normal fan. Why is that? Because, you know, in this case where we have only constant coefficients, meaning only zeros as coefficients, the functions, the pieces of your affine linear functions, well, they are not affine, they are honestly linear, right? So they really give you this linear thing, and the region where two fit together precisely corresponds to the cones where the face is not just a vertex, yeah? So something deeper in the stratum somehow. Okay. So that's already good, because this gives us a way to understand the combinatorics of at least special tropical hypersurfaces in terms of outer normal fans of dual polytopes. Now we want to sort of generalize that. How do we do that? First, I have to give you a certain construction, which is the dual Newton subdivision. So again, we take our tropical polynomial like this, and then we consider the convex hull not only of the alphas, but we take the alphas and another coordinate, so this in the support of f times r, such that that last coordinate is less than or equal to the coefficient a alpha. Yeah, because you see in what we had here, all the coefficients were 0, right? So they didn't play much of a role. The Newton polytope was enough to understand the combinatorial structure of the tropical hypersurface. But if the coefficients are not all 0, they should better play some role. They have to play a role, right? So if you're shifting around your linear functions to be affine linear, this has to play some role. And this can be controlled precisely by sort of adding those coefficients as heights, as last coordinates to our Newton polytope. Yes, please.
All coefficients being 0.
Sorry?
The alpha. The coefficient is alpha.
Alpha is the exponent vector. I'm using the same notation here.
Has to be a tropical phenomenon such that all coefficients are 0. By
Yeah.
coefficients, you mean the A alpha?
Yes. Yes, yes, that's right. Coefficients are the A alpha. Yeah, but now I'm assuming they are not necessarily 0. Yeah? Okay. So I take this convex hull, and then I project. I'll do an example in a second, so you'll see better. I project the upper faces to the Newton polytope of F. And what you obtain is the dual Newton subdivision of F. Okay, yeah, let's do that, and let's do that maybe in a two-dimensional picture already. So let me take the following tropical polynomial. 0 plus 0 times x squared plus 0 times y squared plus 1 times xy plus 1 times x plus 1 times y. So what am I doing here? Let's first understand the Newton polytope. So this gives me the point 0, 0. This is the point 2, 0, 0, 2. xy is 1, 1, and then x is here and y is here. So this is my Newton polytope that I'm talking about. Now, this convex hull here is not happening in 2 space, so I'll have trouble to really seriously draw this, but it's happening in 3 space, and I'm adding heights, so to say. And those heights are going to be everything that is less than or equal to the coefficient. So let's write down the maximal heights that we have. So those exterior points, they all have coefficient 0. So the maximal height is 0. And then those middle points, they get height 1. And now I hope that you have some geometric intuition and can sort of view this in 3 space, even though I can't really draw it in 3 space. What is happening in 3 space? So let's imagine, this is flat now, and this is our third coordinate. I'm calling it a height, but since I have to draw on the blackboard, let's imagine this is the height, right? Okay. And so this means those 3 points, I will let them stick on the blackboard, but I take those 3 and I erase them. Yeah. Can you sort of see the convex hull? And can you project the upper faces down to the Newton polytope? What do you see, actually? Yeah, I see some people pointing already. You precisely see that triangle, yeah? So this sort of looks like a roof in 3 space, right? And this triangle part is sort of the upper part of the roof. And then this triangle is what is bent like this, down from the roof. And this is bent like this. And this is bent down like this, okay? And this is what we call the dual Newton subdivision of this polynomial. And I claim that the dual Newton subdivision is very useful to understand tropical curves. So we have the duality theorem, or let me write it as the duality theorem. And let me restrict to 2 variables just for simplicity of notation. But of course, an analogous thing holds in for any dimension. Any number of variables, a duality theorem works. So the statement is the tropical hypersurface associated to F is dual to the Newton subdivision. Okay, what does that mean? In the following sense. So the vertices of my tropical plane curve, the vertices correspond to polygons in the subdivision. The edges of my tropical plane curve correspond to orthogonal edges. And the connected components of R2 minus the tropical curve, they correspond to the vertices of the subdivision. Yeah, more precisely, a polygon with vertices alpha 1, alpha 2, alpha 3. Yeah, so you can think of those as exponents in your tropical polynomial. The exponents corresponds to points in the Newton subdivision. They may be vertices of the subdivision. A polygon with these vertices yields a vertex of my tropical plane curve, which satisfies the following equalities and inequalities. I need A alpha 1 plus, well, let me just write xy times alpha 1. That should just be the Euclidean standard product. The alpha 1, remember that's a vector in n to the 2, right? It has 2 coordinates, first for x, second for y, plus xy times nothing plus. Take it back, equal. A alpha 1 plus xy alpha 1 equal A alpha 2 plus xy alpha 2 equal A alpha 3 plus xy times alpha 3 is bigger or equal to all other terms. Yeah, and the thing is, so as soon as you have 3 vertices of a polygon in the subdivision, and you write down those equalities, you can solve them uniquely, of course, because we're talking about affine equalities with 2 variables. Yeah, so there's a unique solution of x and y. But then these inequalities, they are not obvious that they are satisfied. Yeah? And this is the question somehow, which 3 pieces of my piecewise linear function actually meet when I take this maximum and then take this, this maximum picture in 2 dimensions, right, or in higher dimensions. Which pieces actually meet and will produce a corner locus that then corresponds to a vertex in the tropical curve? This is precisely governed by the dual subdivision, yeah? And so as soon as you have vertices that correspond to a polygon in the dual subdivision, you are guaranteed that these inequalities can be satisfied, that you will find a point xy that then also satisfies these inequalities. And that is nice, because this helps us to actually draw tropical curves very efficiently. Yeah, remember earlier for this tropical line, we tried to understand the piecewise linear function, max of x, y, and 1, and try to understand the corner locus. And that worked because it was a small example. But if you now look at this piecewise linear function and I ask you to do the same thing, that's no fun, right? So you have 6 pieces and you have to understand how they come together and which meets which and so on. It's really terrible. You don't want to do that. So the dual Newton subdivision really helps you to organize this in a very nice way. So how do we do this? Well, yeah, let's actually talk about this example. So we have 4 polygons, which I want to call, let me just label them. 1, 2, 3, 4. And for those 4 polygons, I can use this fact to compute the corresponding vertex of the tropical curve. So for the polygon labeled 1, what are the equations I have to solve? So I have 3 vertices, so I need to set the terms corresponding to those 3 vertices equal. What are the terms? Well, this was the term 1 plus x, right? Written in the usual way, yeah? This was the term 1 plus x plus y. And this was the term 0 plus 2y. So we solve for x and y, and what do we obtain? X is 0. And what is y? 1, right? Okay, for 2, yeah, maybe I don't want to write them all down, but let me do 2 again. So 2.
Alpha 2, what is alpha 1 there?
Alpha 1 is the coefficient, the exponent of this term. So alpha 1 is 1, 0, alpha 2 is 1, 1, and alpha 3 is, sorry, I said 1, 0, 0, 1, of course, I mean, and this is 0, 2. Yeah? And then the coefficient, so, yeah, so this is, this is A alpha 1 times x to the alpha 1. And when I say x, I mean multi-index notation, of course. So I should write it as x to the alpha 1, 1 times y to the alpha 1, 2 with those 2. Does that help? Ah, okay, great.
1 plus x there is 1, and 1 plus x plus y is 2.
What?
So in 1,
In 1, yeah.
1 plus x equals to 1 plus x plus y.
That's right. So you're saying I mixed it up somehow. What? Oh, it's 1. This is why I mixed it up. Yeah, and then the solution is still correct, right? Okay, thank you. Good. Okay. Yeah, let's get the second one correct now. Yeah. So the second one, we have 3 vertices. They have 3 exponent vectors, which are 1, 0, 0, 1, and 1, 1. These are my 3 alphas. Yeah. The coefficients are always 1. So I have 1 plus x plus y equal 1 plus x equal 1 plus y. And that means x is 0, y is 0. Okay, now I think this is getting boring. You could do it for polygon 3 and 4. You don't need me to do it. And the solutions we obtain are going to be as follows. So we obtained the point 0, 0 already. We obtained the point 0, 1 for this triangle. You're not going to be surprised. This is very symmetric. This will give us the point 1, 1. And then 4 will give us the point minus 1, minus 1. So these are the vertices of my tropical curve here. And then what are the edges? I just have to draw orthogonal edges. Because by duality, this is what is required, that the edges correspond to orthogonal edges. And then this is my tropical curve. And you can sort of think of this as, and this is precisely what it is, local outer normal fans. So let me draw the subdivision a little bigger. And then I can try to draw the dual picture sort of inside here. Yeah? So I sit inside and draw the codimension skeleton of this outer normal fan of this small polytope here, right? And then I draw a vertex here, and now I draw the outer normal fan here. Okay, same here, same here. And then you see I get this picture. Yeah? What you have to be aware of, however, is that this dual Newton subdivision is really, it only takes care of the combinatorics of my tropical curve. It does not take care of the precise positions of the vertices. The precise positions I can compute with such inequalities, but this is not something inherent in the dual Newton subdivision. That has to do with the actual choice of coefficients. And depending on your choice, you know, it may be that you have the same dual Newton subdivision, but a curve that sort of maybe looks like this, right? It would still be dual to the same Newton subdivision, but you couldn't really draw it inside like I've done. This drawing inside is more to sort of understand the relation. It's not that you should expect all your tropical curves to live inside a dual Newton subdivision. That's not the case. They're only just dual, yeah? But this is what duality means. Okay, and I want to give you an idea of how to prove this duality theory without giving a detailed proof. So let me just say idea of proof. And the idea of proof is that you're sort of pretending that there's another variable around, such that the coefficients, so you're sort of boiling it all down to the constant coefficient case, with which we already felt sort of comfortable, I hope. You're boiling it down to the constant coefficient case by pretending that those coefficients that you have, which are not all 0 now, actually are exponents from another variable that I introduce. Yeah? So I introduce a new variable. Oopsie. Introduce new variable. Let me call it t. And I think of a new polytope that I call f tilde as the tropical sum of t to the coefficient a alpha times multi-index notation again, x to the alpha. Yeah? And then this convex hull that I've been talking about here is precisely the Newton polygon of this thing, right? And then this is now a constant coefficient tropical polynomial, yeah? And so I can use my proposition that states that the tropical hypersurface defined by this guy is going to be precisely the codimension 1 skeleton of this, which is its dual Newton subdivision, right? And then what I do, so then v trop of f tilde, which now lives in r to the n plus 1, of course, yeah, is the codimension 1 skeleton of the normal fan. I forgot my own notation of the normal fan of the Newton polytope. I think that is correct, right? Newton polytope of f tilde. Yeah. Okay. And then and then we have this normal fan now living in 1 dimension higher. And what we do is we slice with the hyperplane given by t equal 1. Yeah, and the slicing with the hyperplane given by t equal 1 will precisely produce the inequalities and equalities we want to have in R to the n now. Yeah? And this will precisely give us the corner loci of this tropical hypersurface defined by F.
So
Then-
basically, each of F is a four-dimension one skeleton of a normal fan of Newton polyton. Normal fan of Newton polyton. Because this four-dimension one skeleton of Newton polyton, or normal fan of Newton polyton.
Ah, thank you. Normal fan of Newton polytope. Coordination one skeleton of Newton polytope doesn't really make sense. Sorry. Thank you. That was a mistake. Thank you. Yeah, that's right. Yeah, and this is the Newton polytope of F tilde, what we have here. Okay, then slice with the affine hyperplane T equal to 1. And this yields V trop of F, now in R to the n, which we can identify with this hyperplane, right? And this relation explains the duality stated in this form. Yeah? Okay, so with that, we already have a good understanding of what a tropical plane curve is, how to draw it efficiently. If I now give you, or if Thomas gives you a tropical polynomial later and asks you in the exercises, draw the tropical plane curve defined by this tropical polynomial, I hope that you'll be all able to do this actually, right? However, it actually turns out that this, viewing our tropical curves merely as subsets of R to the 2 is not quite sufficient. We want to have some more structure, and the structure is sort of given by duality. So one task you could also do later is to draw two different dual Newton subdivisions, or to find two different tropical polynomials that have different dual Newton subdivisions, but that define the same tropical plane curves as sets, right? And that tells you, if you're forgetting the dual Newton subdivision, you're sort of forgetting too much. You should keep something more in mind that's coming from the dual Newton subdivision, and that these are weights. Now we want to add weights, sort of. So what we know so far is that our tropical hypersurfaces are going to be polyhedral complexes in R to the n. Tropical plane curves are just piecewise linear graphs in R to the 2. But now I want them to be weighted polyhedral complexes. Tropical hypersurfaces are weighted polyhedral complexes. And you want to add weights for the top dimensional strata somehow. And the weights are given by the dual Newton subdivision. The weight, okay, let me slow down. The weight of a top dimensional cone, top dimensional cell, sorry, it's not a cone, cell of a tropical hypersurface So the top dimensional cell of a tropical hypersurface is a codimension 1 cell in the normal fan, in the normal fan of the Newton polytope, or extended Newton polytope if you want. A codimension 1 cell in the dual fan comes from an edge of the polytope. Yeah? So that you can view this as the weight of the corresponding edge in the dual Newton subdivision. And we define it to be the lattice length of this edge. So let me draw a picture. So imagine this is my Newton polytope and also my dual Newton subdivision. So for example, my tropical polynomial could be just 0 plus x squared plus x times y, so constant coefficient case, all coefficients are 0. I'm not raising anything, everything stays 0. If I project, I get just the same picture, right? That's the easy constant coefficient case. And how does the dual tropical curve look like? Well, it's just a fan right now, 3 rays in r to the 2. and a vertex at 0. And then the non-trivial weight that I want to add is the downstairs weight. It has weight 2. This edge has weight 2 because the lattice length of this edge here is 2. Yeah? These have lattice length 1, and I usually don't write down a 1. Trivial weight is something that we don't write down. We only write down non-trivial weights. And those weights are something that we should keep in mind, because if you write down the weights, then from the tropical curve you can go back to the actual dual Newton subdivision. If you don't do that, the dual Newton subdivision is not unique. Yeah? Okay. And this brings us to the following theorem, which is the balancing condition. And the statement is, if I have a tropical plane curve, and I'm now drawing a local picture around a vertex. So here's a vertex. Some edges leave this vertex, and then, you know, the tropical plane curve could continue and do whatever, but I don't care. I'm focusing on this vertex. And then I have adjacent edges, and I have weights for the adjacent edges. And we call them M1, M2, and so on. These are the weights. And I have direction vectors, primitive direction vectors. Primitive direction vectors. So in set 2, of course, right now. And then the balancing condition says that the sum over the mi, the vi, is equal to 0. Let's check this here for the tropical curve, which is just a fan and has only one vertex. What are the primitive direction vectors? This is 1, 1. This is minus 1, 1. And this is 0, minus 1. And now 1, 1 plus minus 1, 1 plus 2 times 0 minus 1 is actually 0. Yeah? And why does this work out? Because those weighted direction vectors times their weight, are precisely orthogonal to the edges in my dual polygon. And the fact that they sum up to 0 just means that the polygon actually closes up. Yeah? The vectors, if I put them one after the other, closes up. That's why the balancing condition holds. Okay, so I want to write down one last theorem for today, which is the tropical Bézout theorem. So those of you who have an algebraic geometry background, of course, all know Bézout's theorem, a tropical curve, algebraic plane curve of degree d and an algebraic plane curve of degree e intersect in d times e points counted with multiplicity. It's famous and it's super helpful also, right? And the good news is that something similar holds tropically also. But to make sense, we first have to define what a tropical curve of degree d is. What is a tropical curve of degree d? Well, just think of what is the Newton polytope of a polynomial of degree d. When we're talking in algebraic geometry about plane curves, then of course we mean projective plane curves, so we use polynomials which are homogeneous in 3 variables. But we can dehomogenize and view those as polynomials in just x and y. And then what does it mean to be of degree d? It means that you get this thing as Newton polytope, right? The thing that has d0, 0d, and 0, 0 as vertices. And we define a tropical curve to be of degree d if this is the Newton polygon also. Yeah? So if, meaning, you know, if this comes nicely subdivided somehow, yeah, then this means that the tropical curve would roughly look something like this. Yeah? So there will be d ends in direction, d downward ends, d left ends, and d diagonal ends, and in the interior, whatever could happen. Like, for example, here, this is a tropical conic, a curve of degree 2. The tropical line is a curve of degree 1, right? So that's the degree. And then we say tropical curves intersect transversally. Transversal intersection if they intersect in finitely many points which are in the interior of edges. So something like this is fine. One point which is in the interior of edges. Something like that would not be fine, because it's only one intersection point, but then it's a vertex of one of my tropical curves, so I don't want this. And something like two tropical lines that overlap in half array, I also don't want. Yeah? Finitely many points such that the point is in the interior of an edge. And if I have, local picture again, imagine I have two big tropical curves, they continue here, and I have one intersection point, which is such a transversal intersection point. Then I can define the intersection multiplicity, and the intersection multiplicity will be the product of the weights. Those two edges have weights, right? Because my tropical curves are weighted piecewise linear graphs. They have weights, and they also have integral direction vectors, v1, v2. And then I take m1 times m2 times the absolute value of the determinant of v1 and v2. Okay, sanity check. If two tropical lines intersect like this, for example, we have this one point of intersection. The weights are 1, right? Because dual to a tropical line is just this Newton polytope. All lattice lengths are 1, so I don't even bother to write down weights. So the intersection multiplicity would be 1 times the absolute value of the determinant of 1, 0, 0, 1. Okay, and that's 1. And of course, we're not surprised, and we wanted that to be true. Okay. And with that, I can state Bézout's theory. Bézout's theorem for plane tropical curves. And just as a hint, this also holds in more generality, so for tropical hypersurfaces of reverse dimensions. But let me state it right now only for plane tropical curves. A tropical curve of degree d and degree e, which intersect transversally, intersect in d times e points, counted with multiplicity, of course. Okay. And I don't want to prove this now for you. I want to just draw, maybe one or two pictures. Well, one picture I have already drawn. These are two tropical lines, two tropical curves of degree 1. They intersect in one point, as we expected. Now let me draw a tropical conic, like this one that we've seen before, coming from the polynomial of degree 2, right? And let me draw a tropical line. And maybe, I'll draw a certain tropical line. This. Oh, what happened? This has a red cap, but it's not red. Okay. Okay, this is my tropical line. And now you see 2 points immediately. You can make the computation. It's totally the same. It's 2 points of intersection multiplicity 1. So they indeed intersect in 2 points, as expected. Yeah. And this example sort of tells you a lot about the proof already. You could use it as a beginning of the proof, so to say, because all I need to do somehow is take this blue line and move it around and make sure that 2 points stay 2 points counted with multiplicity. And if I move this guy around, of course, it will move over vertices of my Plaque curve. But the vertices of my Plaque curve, they satisfy the balancing condition. And this is the main point. If you impose that, if you use that, then you will see that this number of points actually stays constant. And this is sort of already the proof of Bézout's theorem. Details have to be filled in, of course. Okay. Yeah, so I think this is precisely the moment to stop for today. Just as a small preview, today we've been completely intrinsically tropical, right? We started with a tropical semi-field. We have not talked about algebraic geometry at all, about usual algebraic geometry, just, tropical algebraic geometry viewed as, hypersurfaces over the, defined by polynomials over the tropical semi-field, right? Next time I want to show you what those guys actually have to do with honest algebraic plane curves, because they're not just mimicking this. The fact that Bézout's theorem holds, it's not just a big surprise because things are nice. No, it has a reason, because those guys actually are degenerations of algebraic plane curves, as I mentioned, and this I want to tell you next time. Okay, questions? Thank you. Yeah.
So where does that multiplicity come from?
Where does the multiplicity come from?
Yeah, the number M1, M2.
M1 and M2 are the weights of those edges.
Why that's the weight?
Why do the weights appear here? Is that the question?
So because you said that the Bézout holds because this comes from geometry.
Yeah.
Which I don't see now. So I think,
This would be asked too much a little bit to see that now. But maybe one way to view this is, let's look at this picture that disappeared. This picture. Okay. And this thing, okay. And now, the fact that this has lattice length 2 means that the curve that corresponds, or any curve that will give this tropicalization as degeneration, will intersect the toric boundary corresponding to this edge of the toric surface in which this guy lives in 2 points, right? And this is why weights show up, put very roughly. Yeah, this locally you have 2 solutions. This is a quadratic equation if you restrict, yeah? So you have 2 solutions. So this is why the weights have to show up. Actually, a more difficult question is why this shows up. I have to admit, this is I don't have a good way to motivate this. This is the toric boundary picture, I think, is very clear. But the other thing is maybe more difficult, yeah. Anyway, proving the tropical Bézout theorem by using the algebraic Bézout theorem is yet a totally complete challenge, a different challenge, yeah? But this is, proving this directly in the tropical world is easy. Proving it by using the algebraic theorem is terrible, because then you have to really understand the translation and understand how intersections tropicalize, and this is actually not easy at all. So this is, you may try if you like, but this is on a different level, so to say. You don't seem super happy with the answer, but I'm not quite sure how else what it's fine? Okay. Maybe we can talk later also. Yes?
I think so the determinant part was annoying, but is there like an easy extension of that to the Bézout theorem for general hypersurfaces?
Yes, absolutely. You need tropical hypersurfaces of complementary dimension. And then, so it's like a mixed volume in the dual subdivision corresponding to the intersection, corresponding to the union. So you take the dual Newton subdivision corresponding to the union of those, and then those points produce precisely the mixed volume of those 2 polygons. Yes?
I mean, it could be a great question, but yesterday Drew said like we can classify rotoric varieties if you also include the torus section according to their friends, and we are seeing some like polytopes here.
Yeah.
They're kind of related to kinds. Like what is
Yeah, that's a very good question. What is the relation? The relation is sort of hidden in what I'm going to talk about, in how usual curves degenerate to tropical curves. But to be completely honest, I will not go through the full program here somehow. But what is hidden? We're actually taking subvarieties of a torus. Yeah? And the tropicalization of the subvariety, which has to be defined, yeah, there's some sort of degeneration. The tropicalization will be, in the constant coefficient case, at least a fan, and the fan tells you how to compactify your torus in such a way that the compactification is nice with respect to your subvariety, in the sense that your subvariety will intersect the strata, as governed by the fan somehow. Yeah, so this has a lot to do with each other, and you can view tropicalizations, tropical curves, as degenerations of subvariety of tori that know something about nice toric compactifications of your torus. Does that help?
It helps. I have further questions, but I think they're too early.
Too early. Okay. Ask next time, please. Okay. Okay, good. Lunch then.